Well, thank you, Anna. It was a really nice introduction for my paper. It's an additional paper about energy efficiency. I hope you're not bored. But I will focus on different points. So yeah, this will be pretty interesting. We already said or asked the question, okay, how about the life cycle, about modernization of elevators? That's also the content of my presentation. And the target is here also always to find not only the best energy efficient solution, but also to find an economical solution. And this is where I'm focusing on this presentation. So, and the frequently asked questions, which I usually hear as a development guy from our sales department, is how high is the energy saving in case of a modernization? Or which energy efficiency class can be achieved, which is usually asked before the installation is done and the measurement can be done. And we know that typical challenges are that elevators are unique copies. So we don't have a label for like for the fridge, which is for every fridge the same. So it depends on the elevator size, usage, and so on. And when you look into literature, you will have very rare measurements which are really comparable of different drive technologies. So usually also the mechanical system, for example, varies, and it's difficult to compare the different drive technologies. And in addition, for the old drive systems, we usually have very less data. What is the efficiency, or what is the inductance or the resistance? We only have the plate, the machine plate, and that's everything what we know about it. And that's the reason why I will present today measurements which has been conducted at lifts where the mechanical part stays the same. And I will calculate and simulate some further results to compare other drive technologies. I will start with the typical modernizations and characteristic of different power consumptions for in high-rise and low-rise elevators. Then I will give an overview about the systems used in the past. And then I will make show up the energy measurements before and after the modernization. And finally, I will show up a comparison between the VDI for 707 and the ISO. So Anna, I'm happy that I can now deliver what you requested, that we also show up the ISO code for our elevators. Let's start typical possibilities of modernization. We can make a full replacement. For sure, we definitely have then the best standby and running demand, but it's usually also the most costly. And what Anna already said, it's also concerning a life cycle analysis, not always the best solution for the environment. That's the reason why sometimes also only the controller is exchanged, which mainly impacts the standby consumption. And where I focus today on is to exchange the drive system by a new drive system which then affects the idle and especially the running demand. Let's start with the main characteristics for power consumption. I have one on the left side here, a low-rise lift with 1000 kg and 1 meter per second. It's visible that, do we have somewhere a laser pointer? Can't see it.
Just like a switch on the side.
Huh?
You can read that as well.
This one? Ah, great. Now I got it. Is that it? Yep. Looks great. So what's visible here, we have only a small acceleration peak. When we compare a high-rise lift here, in comparison, a typical example for 6 meters per second, 170 meters travel height, we had a much higher acceleration peak to accelerate all the moved masses. So this peak is much higher than the power consumed during constant load. same applies also for the energy which is here, an inverter drive with energy recovery. Coming now to the systems, drive systems which has been used in the past, and just giving a short overview. We have, especially for the older elevators, a lot of two-speed machines. We have phased fire controllers, or ACVD drives. Where I'm focusing today also is especially on the Watt-Leonard drive. It's also called a motor generator. And then I will go on with the DC machine thyristor controller, and also with, especially, I will compare it after the modernization with gearless machines with a variable frequency and a variable voltage inverter. I want to remark already at this point that there's also in between the different drive technologies, there's a huge differences between the energy efficiency. For example, given by different efficiency of the gearboxes, of the machines, inverters has also improved a lot in the last 20 years. So let's focus first on the first technology, two-speed drive. How does it work? We have just two windings, and a slow speed and a fast speed winding, and we start with a slow speed, then switch hard to the high speed winding, and then switch again to the slow speed, resulting that it's more abrupt. So if you want to have a more smooth motion, then you usually apply a high mass at the traction sheath so that the motion is more smoother. Getting for the next one, a phased fire controller. It's based on, usually has a thyristor, also thyristors inside, and they cut the sine at different phases, and thus they are able to control the speed of the drive. For braking, they have an additional DC winding where they are able to brake the system. So, but this means that they also need, for braking, they need energy. So it's still even more energy is wasted. Going to the system which I will focus or will show measurements later on is the Watt-Leonard drive. There we have included an induction machine, a DC machine, and a DC generator. So the induction machine converts the electrical energy to mechanical, and the DC generator again from mechanical to electrical, and then the lift motor then is moving the final elevator. So we have a 3 times conversion here, so you can be sure that this is having a lot of losses for these conversions. Then the next improvement was, which has been installed since the 1980s around, is then that the motor generator was replaced by a silicon controlled rectifier, and then to drive the gearless DC machine. The main disadvantage here is especially the high reactive power applying, and also the energy efficiency is not as good as for VVF drives. Focusing now, what's currently state of the art? VVF drive, either used with geared or gearless machines. They started to install it since the 1990s, and it's used with induction machines or permanent magnet machines. And it's possible to have also the regenerative mode. So to show first the topology without regeneration, we have here the diodes at the grid side, which converts from AC to DC, and then we have a transistor, IGBTs, which then converts from DC to alternative voltage, alternative current. For regen, it's more or less the same topology, but just we have also transistors at the grid side, so that it is possible also to feed back the energy to the grid, and not like in this case where the energy is dissipated over a brake resistor. How does the VVF inverter produces the sine? It's done by a PWM, by pulse width modulation, and depending on the width of the pulses, the sine is created and thus feed it to the machine. Coming now to the energy measurements, which have been performed before and after the simulation. It was a lift with around 50 meters travel height, 2.5 meters per second, and it was originally a Watt-Leonard drive and then has been replaced by an induction machine with VVF inverter, and one with regeneration and one without regeneration. So we have in total 3 types. Showing up the first type, at the left side you see the energy consumption or the power consumption of the Watt-Leonard drive. In black it's the power consumption, and in the blue dashed line it's a reactive power, and in red you see the speed. Showing now on the right side the same mechanical system after the modernization, but with a non-regenerative inverter. So what are the main differences? You see a very high reduction of the acceleration current, about 50% less. You see, in addition, a much smaller idle demand, because the Watt-Leonard drive has here around 8 to 9 kilowatts idle demand. And also, the reactive power has been reduced significantly, giving a total energy saving in this case for 36%. Second example, also on the left side again the Watt-Leonard drive, but now on the right side included the regenerative drive, so meaning that the energy is regenerated. You see also the Watt-Leonard drive is a regenerative drive system, but due to the 3 times conversions, the energy efficiency and the feedback energy is pretty low. And if you compare here the total energy demand, we already talked here about an energy saving of 53%. In addition, the power factor has been improved further, because there's almost no reactive power anymore visible. Coming now to, this has been conducted in 1995, yeah? So it was the VVF inverters of the first generation, and it was an induction machine. Meanwhile, permanent magnet synchronous machines are used, and also in the semiconductor industries we have much faster switching IGBTs, which have much less losses, resulting now into the current results. Yeah, I have again here on the left side the results from 1995, and now taking the results from 2014, seeing here that we have also a further reduction for the power peaks, and additionally, and also we have a small percentage higher energy recovery than we had in this system. So overall, in compared to the Watt-Leonard drive, we can save here around 80% energy during running. Yeah? During idle, it depends how high is the usage, which I do not consider here. Coming to my last point, especially prepared for Anna, the application of the ISO norm in comparison to the VDI for 707. Just as a wrap up, what is done in the VDI for 707, it's done a reference trip with an empty car in down and in up direction. This energy is measured. Afterwards, it's divided by 2 and the travel height and the load, multiplied by a factor, and then you get the specific travel demand. You wait for 5 minutes, and then the standby demand is measured, and out of this, the total annual demand is calculated. Going to the ISO, 4 trips are done, so a short and a long cycle. Out of this, the running demand is calculated depending on the number of landings and depending on the usage category. There's an average travel distance, which then results again in a specific running demand. Furthermore, for the non-running demand, also idle and standby after 30 minutes is considered, and out of this there's a mix calculated depending on the usage category. How is then the annual demand calculated? We have on the one hand side this specific travel demand multiplied by the running time, and we have on the other side the standby demand depending on the usage category. If we now look on the ISO norm, we have much more factors in it. We see that also the number of starts and especially the load factor, which Anna already mentioned, applies, is a factor. And additionally also, especially for the time of idle, is considered also for the annual demand calculation. Looking now at the comparison, at first I have prepared two elevators. At first a low-rise elevator and at second a mid-rise elevator. 1 meters per second, 1000 kg payload with 3 stops. So we get then on the right side here the comparison depending on the usage category. We have here in blue the ISO and in green the VDI. So for this low-rise elevator, especially for the usage category 4 and 5, we have a high deviation between it, and the ISO has the more realistic results concerning to the reality. Now it's getting interesting. If you compare now the energy efficiency class, which is achieved in this elevator, you see in the VDI you always get an A. You see in the ISO for the usage category 1 to 3, you get a B. So just as a remark, it will be pretty challenging to get an A for low-rise elevators in the ISO code. I mean, just why I say this, why challenging? It's a regenerative drive system with a permanent magnet machine, and also idle and standby consumption is quite well already. If you look for the mid-rise elevator, we have a travel height of 68 meters and a speed of 2.5 meters per second. And you look there, the differences of the ISO and the VDI, you see the differences are much smaller. Even the ISO now predicts a higher annual energy demand than the VDI, but the curve looks pretty similar. Still, there is a difference of 500 to 1,000 kilowatts per year, kilowatt hours per year, which is not nothing. So, but the curve and the behavior of these norms are very similar in this case. Looking now in the energy efficiency classes, everything is in A. So also, or especially here, there will be concerning the energy efficiency classes less differences concerning if you get an A or a B. Coming to the conclusion, I just showed up that we have with a modern VVVF drive up to 80% energy savings in compared to an old Bad Leonard drive, and that it is also concerning not only concerning energy efficiency but also environmental impact. A good solution just to exchange, for example, the drive system instead of throwing away the whole metal sheet of the mechanical system of the elevator. We have a significant improvement also seen for the VVVF drive since 1995. And what I mentioned is that the ISO considers more parameters and forecasts the energy efficiency or the annual demand more accurately. But especially in low-rise elevators, it's also challenging to get the A. Thanks for your